This is a sample of a spike that's occurred during the interictal seizure. And you can see that with three different mathematical transforms, we can project this signal to time frequency domains. But in these three transforms, we can see that the wavelet transform can better show the differences and can better show the details of the variation of the signals in the time frequency space. You can see the different types of temporal lobe epilepsy. You can see that these two signals in the left and right figures are totally different. That's very crucial, and that's very hard that a neurologist observe and diagnosis that these two are from the same root. These two are from the same category of seizure. That's why the visual inspection is very hard and cannot help us to diagnose accurately. It doesn't work? Oh, okay. Jacksonian march is a type of focal epilepsy that I just show you a sample of it, that you can find the seizure type patterns in the EEG signals, and these patterns can be classified with artificial intelligence techniques that we have done it in the Namazi Hospital of Shiraz, and we could classify. We have classified these four types of seizures with a high accuracy that was acceptable for an experienced neurologist. Again. Okay. This is a sample of EEG signals for a patient with Alzheimer. You can see that the signal behaves completely irregularly, and you cannot observe any type of pattern through the signal. But when you transform it into the time frequency domain, you can see that there are some red points that show the high variations related to the Alzheimer's disease. Alzheimer's disease behaves like MCI disease, and there is a very high overlap between the diagnosis of Alzheimer's disease and minimal cognitive impairment disease. Both are neurological diseases, but patients takes different medications or different drugs. You can see that when we project these signals with artificial intelligence techniques into the frequency domain, we can see the differences between the MCI and Alzheimer's disease and healthy control and people with Lewy body. We can classify these four types of patients. Age of autism. You can see that autism behave like a seizure. You can see a lot of seizure discharge through the signals of autism patients. As I told you, classifying the different types of neurological disease just by observing by eye to the signals, just by visual inspection, is very hard, but artificial intelligence can help us to diagnose these diseases. This is the research that has been done by us that shows that we classify different severity of autism. There are 14 patients with autism, and we classify the autism with mild severity, with moderate severity, and with severe state. As you see that the sample entropy of these both channels that are marked in the figure are separated from the samples of other. You can classify them with more than 90% accuracy, as you showed it, as you show in this figure. This is a sample of schizophrenia and a healthy subject. You cannot see any difference between their signals, but we can classify them by artificial intelligence techniques. As you see, the above figure is a EEG signal of a control subject, is a healthy normal person, and the below shape is the schizophrenia for the patients with schizophrenia. As you see in the figure, we show the brain map of a person with schizophrenia and a person with normal state, okay? And in the above figures, in the upper figures, you cannot see any big difference from them. But in the lower case, you can see a better type in the occipital part in the behind the brain in this area. In this area, you can see a better difference between two diseases, and we made it by particle swarm optimization on the frequency bands to find which type of frequency bands is optimum for detection the schizophrenia against the normal subjects. You know, there are in some type of neurological, neurotical disease and psychiatric disease. Neurotical disease is like depression, is like obsessive compulsion disorder, is like trauma, post-stress trauma. But psychiatric disease like schizophrenia, you can see it, deformity in the brain of the people. You can see these two shapes that show that the brain, the CT scan of a normal person and a schizophrenia person. That the sinusoidal cavity of the schizophrenia patients is much more bigger than a normal person. But you can diagnose them by taking the EEG. That's much cheaper and take a sooner time compared to taking CT scan from them. These are the papers that each of them gets more than 100 citations about the classification of schizophrenia and healthy patients in the raw state, in the idle state, by processing the raw EEG signals. EEG of depressions, you can see that in the above figures, there are the EEG signals belong to the normal patients, and the below shapes these signals is for depressed persons. You cannot see any difference, any big difference between the patterns of these two signals. But with the help of artificial intelligence that we published it in 2021 in the very valid journal, we classified these two diseases, and also we estimate the Beck score with a very high accuracy. As you see that the proposed method provides the mean square error plus minus standard deviation of 5.64 in comparison with other rivals. That's much less than them, less error than, compared to them, and it shows the superiority of our method compared to them. In this method, we use 3 layers of convolutional neural network and 2 layers of temporal convolutional neural networks together. It's a 5 hybrid convolutional neural network and temporal neural network together, and you can see the performance. In another paper that's recently published in 2023, we classify the depressed patients and normal patients with different level of severity with the help of LSTM, which is a neural network, which is a deep neural network, and a spiking neural network, which is the second generation of neural networks. You know, spiking neural networks takes a spike in input and output. There is a difference between the spiking neural network and the artificial neural network. The information is encoded between the pulse duration in the spiking neural network, and when the neuron wants to be fired, some spikes in a low duration should be imposed to a neurons that can fire it. And the type of learning it is STDP. That's very different from the back propagation that's used in the normal neural networks. You can see the diagram of our work. The EEG signals are encoded into these signals, and these signals are trained by a spiking neural network. The left figure is the spiking neural network that is not trained, but the right side is the spiking neural network that's trained. And then we can see that these trains are applied to a LSTM long short-term memory network, and we could classify them in 4 different classes. You can see the different patterns that the spiking neural network provided for us, and these 4 patterns are totally different. It shows the mild, no depressions, moderate depression, and severe depression for us. That's we could classify them with a good accuracy. Another application is estimating the depth of anesthesia. When a patient goes to the anesthesia, we want to measure its depth online with the processing of the EEG. As you see that the channels of EEG are located in the forehead of the patients, because some patients might have a brain surgical, and in the brain surgical, the upper part of the head is disattached from the brain, and therefore the signals are located in the forehead of the signals, and it gives a number between 0 to 100 to us. 100 means completely consciousness, and 0 means death. And you can see that with a convolutional neural network and by LSTM and attention layer, we could find a better mean square error, and we could estimate the depression, the depth of anesthesia score with a very high accuracy. These are the index that the BIS gives to us, and the curves that our deep networks could estimate. That you can see that it follows the patterns completely. And you can see that the papers that we have published in the area of estimating the depth of anesthesia. My friend told me that my time is up. I don't know how can I can finish it. No problem. Okay, thank you very much. You are welcome.
Thank you, Professor, for the valuable information. شكرا لك بروفيسور على هذه المعلومات المهمة حول تداخل الذكاء الاصطناعي في مجال الطب بتشخيص وإيجاد الأدوات المناسبة، وحتى النسب والتعامل مع حالات الشيزوفرينيا، انفصام الشخصية، التوحد، السكتة القلبية والجلطة الدماغية والأمراض العصبية وغيرها من الأمراض المزمنة وحتى حالات الإحباط. بدون انتظار نستقبل الآن رئيس جامعة تكنولوجيا المعلومات والاتصالات الأستاذ الدكتور عباس البكري على المنصة، متفضلاً. لتقديم درع الجامعة تكريماً لمعالي وزير التعليم العالي والبحث العلمي الدكتور نعيم العبودي، فليتفضل. وتعبيراً عن امتناننا لحضورك الكريم لمؤتمرنا الدولي لهذا اليوم، هذه بقة ورد بسيطة. لو سمحت معالي الوزير أن تبقى على المنصة لتكريم أبرز مجموعة من الباحثين المبدعين لنيلهم لقب أفضل البحوث. نبدأ بالباحث الأول عمار طعمة نامل في بحثه عن عنوان Optimized Intelligent PID Controller for Propofol Dosing in General Anesthesia Using Quality Optimization Algorithm from Iraqi Commission for Computers and Informatics Institute for Postgraduate Studies. الباحث الآخر صابرين وحيد كاظم for the title Enhancing the Performance of Wireless Body Area Network Routing Protocols Based on Collaboratively Evaluated Values from Mustansiriya University. And then طيف العبيدي for the paper title Face Identification System in Transformed Domains over Secure Communication Channel UOITC from our university. نتشرف أيضاً بتكريم باحثين keynote speakers Professor Riza Bustani from Shiraz University, Islamic Republic of Iran, for his research on AI in medicine. And also, we are honored to receive Professor Haidar Samad from Shiraz University, Islamic Republic of Iran, for his research on artificial intelligence and data mining. الشكر الجزيل لمعالي وزير التعليم العالي والبحث العلمي الدكتور نعيم العبودي، والشكر أيضا للأستاذ الدكتور عباس البكري رئيس جامعة تكنولوجيا المعلومات والاتصالات. شكرا لكم. And now we proceed to our next keynote speaker and his research. Our keynote speaker, the next keynote speaker, he was born in Baghdad, Iraq, and he received the BSc degree from the Isfahan University of Technology in Isfahan, Iran in 2000. And he has MSc degree from the Sharif University of Technology, Tehran, Iran, and the PhD degree from the Isfahan University of Technology in 28, all in electrical engineering. He joined in 28 Shiraz University as a faculty member, and now he is currently a full professor in electrical engineering with the School of Electrical and Computer Engineering of Shiraz University. Now, his main research interest is in the application of these DSP techniques in power system, such as protection and power quality. He has supervised 17 PhD and 43 MSc theses. He has 136 published papers in Q1 and Q2 ISI journals and 63 conference papers. Please, let's welcome our Professor Haidar Samit from Shiraz University, Islamic Republic of Iran, for the research on artificial intelligence and data mining. Professor, there you go. هي تشتغل more effectively over there.
صح.
Okay. تحبي عقب بحثك على هاي الشاشة أفضل لك لو تبقى على هاي الشاشة؟
ما يفرق.
ما يفرق؟
Okay. Assalamu alaikum. Good morning, ladies and gentlemen. It is my pleasure to be hosted by my mother country, Iraq. After we departed from Iraq when I was 4 years old, 1982. I'm a full professor now in Shiraz University in electric power engineering. And here I'm presenting a novel revolutionary method which can solve the big data problem in power systems, or especially in smart grids, which is the analytic time series load flow. The contents are a definition of the smart grids. Then we go to the big data and smart grids. Then we have two examples that how fast the power loads can be changed over time. One example are about our records from the Manjil wind farm, is the northern of Iran. And the second one is from a very big power load which is in the Mubarak Steel Company, electric arc furnaces. We will show that how fast our laws are changing, which results in a huge data set that we have to deal with. And then we will go classic load flows, which are started from 1956,
And here we will give you a novel load flow which can solve the big data problem in the classic load flows, which is the analytic time series load flow. And we will have two examples for this new kind of load flow in power systems. So we have the classic traditional power system, which we have communication between the large loads and large substation and the control center. But in the new power system, which we call them the smart power grids, this communication between the loads and between the center is more. So here every load, every power consumers, every small power consumers can communicate the data to the center, which results in the big data problem. So the smart power grids simply refer to electrical grids powered with modern technologies such as big data, sensors, wireless modules, and monitoring systems, which make the power grids more efficient. So the biggest difference between the traditional power system and the smart grid is the communication between the loads and the renewables with the central station. So the big data problem, we have these 5 issues. The first one is the value, the huge value of the data we have. And the second one is the velocity of the data that we get from the consumers. For example, in the power quality problem in power system, we have to record the data, or the consumers should transfer the data every 20 milliseconds. It means 50 times per second. They should communicate the data to the center. So for example, for every 1 second we have 50 data. Every 1 minute we have 3,000 data for one consumer. So if you assume that we have 10,000 consumers, how many data will we have in 24 hours? It will be very, very big set of the data. So the volume, we have the velocity, the speed of the data, the variety of the data, the large diversity of the data sources and formats of the data. Also the fourth one, the quality of the data, how much we can transfer the data, and value of the data, and what we can do with this data. These are some records that I recorded from Manjil wind farm in north of Iran. In fact, my specialty is analyzing the very short time variations of the renewables and also of the loads. There are a few persons that work in this field. So here you can see the variation of the power, active power and reactive power of a wind farm, which they are change every 20 milliseconds. They change every 20 milliseconds. So here we have a very fast changing load in the system. This example is for a wind farm. I have many papers in this field and analyzing the very fast changing load of the wind farm. Here are some of the papers. The second example is for the electric arc furnaces, which we have in Iran many of the electric arc furnaces. The largest ones are in Isfahan. Mubarak Steel Company, which maybe you know the Sepahan football team, it is from the Mubarak Steel Company, and Zobahan. And most of my research are with the Mubarak Steel Company. Here we see current and the voltage of this very big load. It is in fact the largest power load in the system, the electric arc furnace. They have 8 electric arc furnaces. Each one, the power of each one is about 160 megavolt ampere. So totally we will have about 1,000 megavolt ampere of a single load in the Mubarak Steel Company. And this load is in fact the worst load in the power system, which import the harmonics to the system, and it is the highly changing load in the power system. It's changed every half cycle, in fact. Every 10 milliseconds it changes. So if we want to control this load, we need a communication system which communicates the data 50 times at least per second. Also, I have many papers in the field of electrical furnaces. Here you can see some of them. So what is the load flow? We in fact teach the load flow in our undergraduate courses. The load flow is solving the power system problem. Every bus in the power system has 4 quantities: active power, voltage magnitude, and voltage phase angle. Every phase in the power system has 2 from these 4 quantities. 2 of them are known and 2 of them are unknown. So in fact we have a complicated problem. We have 2 n equations. N is the number of buses of the power system. We have 2 n equations with 2 n nouns and with 2 n unknowns values, which should be solved. It is a very classic problem in the power system, which started in the first paper published is in 1956, which solved the power system by coming the early computers to the system. The problem there is getting one snapshot of the data in one instant. We take the data from all the buses and solve this problem, one snapshot of the time. But if we have a changing quantities, all these quantities are changing by time. So how we solve this problem? They can solve it by every second, every instant of time, solve it, the problem as a new problem, but it will take many time and it's very complicated. So the first load flow is published in 1956, and after that till this time we have many papers published in this field which solve this load flow, which we name it the deterministic load flow. And if we have a changing quantities, electrical quantities, we should repeat solving this load flow for every time, for every instant. So the second kind of the load flow is published, or it is introduced in 1974 as the analytic probabilistic load flow in 1974, and after that time till this day we have thousands of this paper which are dealing with this kind of load flow and solving it. In this load flow, they treat the load as a probabilistic quantity. And in this load flow problem, the input are the PDF parameters, are the probabilistic density function of the known parameters, and the output of this load flow are the PDF parameters of the magnitude of the voltage and delta, or the unknown quantities, which is I said it started from about 50 years ago. But the problem here is they missing the time. Here in the probabilistic load flow, they are missing the time sequence between the data they get. They put the data in one fact holder, and they dealing with the data. So I here show the problem of the probabilistic load flow. In fact, it becomes